Hi, my name is Mike Smith, and I'm going to be talking about Detector building for the 2021-22 Science Olympiad competition. We're changing the probe this year from a temperature probe to a conductivity probe, so I wanted to cover some of the bases in this presentation to help you make that transition. And so one of the first things I want to talk about is the content or my intent in this presentation. We want to look at the focus of the task itself. We want to look at resources and support that the team can use, key elements and rules changes from the previous event, topics and tasks that the team should know and be able to do, especially when we look at the written test, and resources to help you prepare for the event. So that will be my intent. And we'll get started with the content of the event. So your team will be building a conductivity device that will be measuring and displaying concentration of sodium chloride in parts per million from 0 to 5,000 ppms. You'll have 3 different water samples to analyze at the regional and up to 4 at states and nationals. Still a team of 2, no impounding. Eye protection not required, and the event will be about 50 minutes. So before I go much farther in this, I want to make sure we understand what's going on. So I'm going to step away and do a little demo, and then we'll come back to the slide presentation. When we talk about conductivity, unfortunately, I think we've all been trained to believe that electricity and water does not go together. And, we've been scared to death of people who've tried to use hair dryers in showers and stuff like that. Reality is that water does not conduct electricity if it's pure water. And I want to demonstrate that to you so you can understand what's going on. So what I've got is a 6-volt battery. I've got 2 beakers, one filled with distilled water and one filled with a saltwater solution at 5,000 parts per million. And I've got 2 wires connected to an LED. The wire that will complete the circuit is now laying on the countertop right here. And what I want to show you is that if I put this into the distilled water, the bulb does not come on because no electricity can go from one probe to the other. So what I'm going to do now is I'm going to take it over and put the same probe into the salt water. Can you see that coming on? Let me get a little closer. The conduction is happening now, not because I'm putting it in the water, but because of the ions that are in the water. Now, the less ions, the less conduction, the bulb would be dimmer. The more ions, the brighter the light. So what we're going to do is we're going to use that principle, but rather than using an LED, we're going to pick up a voltage reading, and we're going to use that voltage reading to display the concentration of the solution. So what our goal will be is build a probe that will have 2 wires that are not touching. When you put them in a solution, based on the concentration of the ions, more or less current will be conducted. We'll have to develop a calibration curve, and then from that be able to determine the concentration of an unknown liquid. And we're limiting this from 0 to 5,000 because it causes too much of a variation if we go a lot higher. So I wanted to start out by just showing you that one of the things that we're always under the concept is that water conducts electricity. In reality, it's not the water that's conducting it, it's the ions that are in it. Okay, I'm going to stop there. So we're going to develop this probe in order to measure these concentrations. Now, the resources we're going to use this year is the same as last year. We can still use any of the microprocessors that we've used in the past. We've added one, the microbit. It's a new device out that we're making available if you choose to use that. And again, the sensor has to be built from fundamental electronic components and not any pre-assembled board. So you cannot go online and find something that's measured. A lot of times they refer to it as total dissolved solids, TDS. So you can't be going out buying something that's going to automatically do this for you. It's got to be from just basic components. and I'm going to show you what I mean by basic components right now. So, well, when I talk about basic components, I'm showing you some example. And again, this is a example. It's not the ultimate and the best way to do it. I'm just saying this is a way that I've played with it. So I've got two wires that are conductors, and I'm going to place them in that test tube and keep them separated so that they are not able to touch and conduct electricity directly. And then when I put my solutions in the test tube of different concentrations, based on the ion concentration, electricity will be allowed to transfer from one to the other. The pipettes and the two-hole stopper are just a way for me to keep the two wires separated from each other. So when I got done, basically I built something, see if I can slip it in there, that looks like this, where the two wires are separate. The little white thing at the end is just to hold them parallel to each other. And the pipettes are just insulators. The rubber stopper is to fit into my test tube. And at the other end, I've got my connection, my wires that are going to go to my microprocessor. So basically, I have a device that is going to measure the resistance of the liquid based on the concentration of the ions in that solution. And there's a lot about the physical makeup of this that is important to know. And you need to do a little reading, a little research. The surface area of these electrodes need to be constant. The distance between them needs to be somewhat constant. The voltage that I'm supplying into this system needs to be controlled. So there's a lot to read about this. So I'm going to give you some resources that TI has put together on some projects in their STEM program that will help you understand more of these components. And this list of components I've got here comes from that particular activity. So when I talk about basic, as you can see, there's no pre-assembled board. There's nothing sophisticated. It's just two pieces of wire that are capable of conducting the electrons, the breadboard for me to make connections, and some insulators just to keep the wires in place rather than touching too early and messing up my readings. The key elements and rule changes is what we've already stated. We're measuring conductivity using water sample, and it's due to the sodium chloride concentration instead of temperature, so that's our main difference. The student still has to build the probe from basic components, so that's not a change, but I just really want to emphasize that because we've had issues in the past where people buy things online that they think are legal and it's really a pre-built probe. And you're still going to be required to have a digital readout that indicates the concentration of your unknowns. And we're also going to continue using the LEDs to indicate specific concentration ranges. And the details of all this is in the rules. But again, we will not tell you those concentration ranges until the time that you're actually competing, so that you have to show that you can program and adjust your program for different concentration ranging. So that part is still the same as the temperature probe was. Things you need to know, and most of this you should learn as you go through the resources I'm going to give in a minute, but you're going to be using something called a voltage divider. And this voltage divider was used last year in the temperature sensor. We didn't make a big deal out of it because it was included as part of the build. It specified what you should build or what voltage or what, excuse me, let me start that again. The voltage divider is an important issue this year because last year we used the voltage divider in the temperature probe, but it was using a fixed resistor that became almost a specified component. This year you're going to have to play with that a little. The Van Hoff factor and electrolysis is part of this because if you put enough electricity into pure water, you can get it to ionize, and you'll start getting readings that are false because you're creating ions. So you're going to have to learn a little bit about electrolysis of water. And the Van Hoff factor deals with the fact that just because salt dissolves doesn't mean that it actually ionizes to 100%. And those two things will probably not be a major issue at the regional level, but as we get higher up, that may be something that you really become conscious of. Again, like last year, analog readings and voltage are not the same. You have to be able to convert that analog reading to a voltage reading. and that will be explained in some of the resources I give you. We're talking about concentration of salt, but concentrations can be measured different ways. So TDS and milligrams and molarity, parts per million are things that you need to be familiar with. The LED itself, how it works, and the process of calibration, how you actually collect the data and come up with some type of relationship between concentration and voltage, and just the basic operation of your device. So these are things that you really need to be comfortable with to be successful, and you will see questions about this on the written test itself. Now, resources. And this is probably the most important part of the whole presentation. Texas Instrument has got a series of STEM activities on their website, and the website is the first link I've given you. That is just rich with all type of background information. That is a great place to start and get comfortable with the TI Hub, which is the microcontroller that I'm going to be using, and allows you to use the calculator as your resource program rather than a computer. It's a lot easier to work with the kids, and it gives them a confidence level right away. I'm going to go to that website to show you the basics of it. So if I click on this website, one of the things I see is something called activities, and under activities I see STEM activities, and that's where I typically go to get ideas. So if I go to the STEM activities, it gives me some options. If you do not know how to program the calculator and you want to learn how to program it, the options right here, the 10 minutes of code, is a rich resource where you can go, and you have two choices. You can do the 84 plus CE, or you can do the TI-Nspire. So whichever platform you're comfortable with or want to become comfortable with, it will take you to several activities and lessons that will build skills, and it scaffolds those skills until by the end you're comfortable with programming the calculator. I'm going to jump over to where it says TI-Innovator Lessons, and this is where we actually start putting components on the hub, and you can see the hub here in the picture. This is our microprocessor that's compatible with the TI calculator. So let me go in there, and then at this point, this is a repeat of the calculator, but you've got here science through engineering design and path to STEM. Path to STEM is where I'm going to go, but again, I encourage you to explore these other resources. They're just my students love them. They're a great resource. So I'm going to go to path to STEM. Again, it's going to let me choose the platform I'm comfortable with. I'm going to choose the CX, and here's our projects. Now there's actually 6 different projects, and each project has a skill, and it has a project. And the skill gives you the skills you're going to need for the project. There's a little video that you can watch that deals with the skill of each of the units. So if you want to learn about how to use the LED and how to use a digital output and how to use the breadboard and how to make connections, you can click on the video and watch this handsome devil just talk to you. Never mind, I'm not going to go there. I'm sorry about that. If you want to learn about the skill, you simply click on the video, and the video will show you a presentation on how to use that particular skill that's going to be used later in the resource. So you get a few minutes of it.
In this video, I'll show you how to assemble an LED circuit and code it to blink the light on and off. Please refer to the Unit 1 Skill Builder teacher notes for detailed instructions. First,
so in each of these videos are going to walk you through the steps. Now the actual files that you would want to look at is where it says download. I usually download all the files, and it gives you both a student version and a teacher version. And the student version is simply the same as the teachers without all the hints and without all the answers. So I recommend that you do Unit 1, become comfortable with the breadboard, and become comfortable with the LEDs and using the hub to interact with the LEDs. The next one that I found very useful was Unit 4, which you're now using the input, the analog input, and the project is how clean is the water. So if you watch the video on this one, it's going to talk to you about a variable resistor because it's using a potentiometer, and it has a fixed resistor, so that voltage divider is explained in this particular presentation. If I download all files and then open those files, and go to the project, because the skill you can look at it's fine, but I'm going to go right to the project. And here it's how clean is your water. I'm going to go to the teacher PDF. When I open that, this gives you basically how to build the probe we're talking about. So here's a great explanation of a voltage divider. And the way a voltage divider works is you have one fixed resistor and you have a variable resistor. Well, in this case, our variable resistor is that probe that we're building, because the actual conduction between these two wires has to do with the concentration of the liquid. And it changes based on the concentration. So what you're getting is a variable resistor. And so by using this fixed resistor over here, it will help you then determine what voltage is being used or voltage drop you get against this variable resistor. And now from that, you can look at how that relates to concentration. So this presentation is not really the Science Olympiad event, but it's a great place to start to get you into the concept of how this probe can be built and used. And they're using some 3D printed parts, and I used rubber stoppers and stuff like that. And then we're going to tie that in with the LEDs. Now, if you notice in this particular presentation, it's telling you to use a 1 kilo ohm resistor. Tells you the branding is brown, black, and red, and that works really good for some concentrations. But what I found is, depending on the concentration, you might want to change that. That's not the perfect resistor for all things. So that was an area of exploration I had to go through. Second, if you put too much voltage in this, and this hub is giving you 3.3 volts, it says it right here, that's okay for certain concentrations. But if the concentration is in certain ranges, that voltage may not be right. It may be too high, it may be too low. And so you may want to play with different voltages, especially as you start looking at the lower concentrations, because you don't want to force the electrolysis to happen. And if you go too high a voltage, you will get that. But these are the resources that you really can use, and it's freeware on the TI website. And I'm going to go back to our PowerPoint. So this right here, this particular link takes you right to the where we were. So that's a quick way to get there, but I showed you could go back by simply taking a link at a time. The last one I found useful because it really is confusing when you start dealing with parts per million and concentrations of called microsiemens or Siemens, which is the conduction unit, or if you deal with molarity. So in the Vernier user manual, they sell a probe called a conductivity probe. And again, this is illegal, but at least gives you a reference to go to. They talk a little bit, let me go down here a little, about how the sensor works, and we're doing the same thing except we're building our own. And then it gets down into relationship between the concentration of sodium chloride in milligrams per liter and conductivity in microsiemens in milligrams per liter. So this chart is what I used to construct my series of unknowns to develop my calibration curve. So I'm including this as a resource simply because this is probably in fact, when I talked to Flynn Scientific uses Vernier's chart here to do their own mixing. So I thought it was a useful resource to give you. All right. Now, just to give you an example of what I did, and I'm just doing this as a final thing, when I put together my tests and I did concentrations, so I did dilutions from 0, you can see the concentrations on the left side, up to 5,000 parts per million. So I did a wide range of concentrations. And then these columns at the top are talking about the resistor that I used, the fixed resistor. So I had 100 ohm resistor, a 1,000 ohm resistor, a 10,000 ohm resistor, 100,000 resistor, because I really wasn't sure how this fixed resistor affected the readings. And I thought it might be interesting for you to see. These were my graphs. And so you can see, I'm going to make a little bit different picture, that each of these color codes were different resistors I used, And depending on the concentration, different resistors, different fixed resistors gave me different resolution. So I expect that students are going to have to do some exploration with different fixed resistors. This will be different on their each probe because that distance between the wires and the surface area will affect the actual readout. So each probe will be unique, but the relationship is something they need to look at, and they need to come up with ranges. And they may actually have to come up with different fixed resistors depending on the concentration and be able to change them out during competition. So these are the things I'm excited for the students to explore. It deals with the concept of what we said is a fixed resistor, and it's very well explained in this presentation, or in the resource. If I can get it to come up again, maybe I can't. But anyhow, in the TI resource that showed how to build a system with a fixed resistor. So I hope that's answered your questions and gives you a start for this presentation. And I'll be glad to answer questions if you need to. So you can refer to my resource slide for my email, and I'd be glad to help.